Hello dear students, in theorem 1a we have studied that for any prime p we can find out integer 1 less than or equal to m less than or equal to p such that mp for some number m between 1 and p, m into p can be expressed as sum of four squares where not necessarily all are non-zero, that means some of them may be equal to 0. Then in theorem 2, that is in Euler's lemma, we have proven that if we consider the product of two numbers where each number is a sum of four squares, then that product also can be expressed as sum of four squares. Now this is the theorem 3, that any prime p can be written as sum of four squares, not necessarily all are non-zero. So using the earlier two results, that is theorem 1a and theorem 2, we are going to prove now this result that every prime p can be expressed as sum of four squares where not necessarily all numbers are non-zero. Okay, so let us start with the proof. So if p is equal to 2, then p can be expressed as sum of four squares in this fashion. Therefore, result is proven when p is an even prime. So now let p be an odd prime. Then by theorem A, 1a, as I said here, in this theorem 3, we are going to make use of both the theorems, theorem 1a as well as theorem 2. Okay, so by theorem 1a, there exists an integer m which lies between 1 less than or equal to m less than p, such that mp can be expressed as sum of four squares. Okay, so there are so by that theorem 1a, there are some values for m which lie between 1 and p, so that mp can be expressed as sum of four squares. So among all such values, sorry, we consider the smallest positive value for m, and that we denote by k. So let k be the smallest positive integer among all values of m. Then therefore kp is the sum of four squares. So let kp equal to x square plus y square plus z square plus w square. Now we have to show that p can be expressed as sum of four squares. So here that means we should show that k is equal to 1. So let if possible k be greater than 1. Then we are going to arrive at a contradiction. But to arrive at a contradiction, we consider two cases, that k is even and k is odd, and we get the contradiction to this fact that k is the smallest positive integer among all values of m. That means we get some value less than k, okay, which suppose n, some value n less than k, so that np also can be expressed as sum of four squares, and there we arrive at a contradiction. That is the whole idea behind this proof. Okay, so let us consider the case 1 first, that k is even. Therefore, obviously kp is also even. Therefore, from equation 1, the sum of four squares is equal to is also even. So since here we consider the four numbers whose sum is even, so obviously there are possibility that either all four of them are even, or all four of them are odd, or two of them are even and two of them are odd. So in either of the cases, what we can see that since since they are either all even or all odd, or two of them are even and two of them are odd, obviously two of them are congruent to each other modulo 2, and two of them are congruent to each other, remaining two are also congruent to each other modulo 2. So we say let xy be congruent to each other modulo 2, and yz be congruent to each other modulo 2. See, x, y, z, w are some numbers, sorry, some notations for denoting the values. So it doesn't matter even if we consider xz or xw are congruent to each other, it's just a notation. So whatever we consider, the theorem is true for all that possibilities. Okay, so here we consider let x and y be congruent to each other modulo 2, and z and w be congruent to each other modulo 2, and therefore obviously there is some so either both x and y are even, or both x and y are odd, or it may happen that xy is even, x and y are even, and z and w are odd. So in either of the cases, what we are going to get, that x plus y, x minus y, z plus w, and z minus w all are even numbers, and therefore x plus y upon 2 and so on are all integers, because since all are even, they are divisible by 2. Okay, so they are now all integers. So now consider the sum of their squares. So when you simplify this, I won't explain this simplification because this is a simple algebra, so you can understand it. So when you simplify this, you get x square plus y square plus z square plus w square upon 2. But from 1, x square plus y square plus z square plus w square notes are written in your book, so you can refer the equation 1. It is on the previous page over here. So I do not go back again. So here x square plus y square plus z square plus w square equal to kp from equation 1. So put that value. So you get k by 2 into p. K by 2 is an integer because k is even. Okay, and therefore here we get an integer k by 2, which is obviously less than k, positive integer less than k, such that k by 2 into p is the sum of 4 squares. So it is a contradiction because we say k is the least positive integer, such that kp is equal to sum of 4 squares. Okay, and therefore here we arrive at a contradiction. That means our assumption is wrong. Therefore we are saying k cannot be even. Now let us consider the case where k is odd and k is greater than 1. Because see, now we have to show that k is equal to 1. So k is odd where k is greater than 1. So now we can obtain the integers a, b, c, d such that we can find out integers a, b, c, d such that x is congruent to a modulo k, y is congruent to b modulo k, and so on. So students, all of you know how do we obtain this a, b, c, d. These are nothing but the remainders when you divide x, y, z, and w by k. Okay, so a, b, c, d are remainders obtained by dividing x, y, z, w respectively by k, such that mod of k, mod of a is less than k by 2, mod of b is less than k by 2. That means here you choose the integer a such that mod of a is less than k by 2. Here I will explain you the meaning. What do we mean? Suppose now we consider x is equal to 13. Okay, and you divide 13 by say k, our k is equal to say 7. So what remainder you are going to get? 6. Now 6 is a number which is greater than 7 by 2, k by 2. Okay, so since it is greater than 7 by 2, over here, see, we have to consider a so that mod of a is less than k by 2. So obviously, here a is not an integer which we want. But then you know that 6 is congruent to minus 3 modulo 7. 6 is congruent to minus 1. 6 is congruent to minus 1 mod 7. Okay, then and 6 is congruent to minus 1 mod 7, and you know that mod of minus 1 is less than 3, or is less than, that means it is less than 7 by 2. 7 by 2 is 3.5. Okay, so accordingly you have to choose the remainder. So if suppose our y is equal to 5, then obviously 5 is congruent to 5 modulo 7. But again, 5 is also greater than 7 by 2. Then what you will consider over here? You consider as 5 is congruent to minus 2 modulo 7. So for B, you have to consider the value as mod of minus 2. Okay, so so that is the meaning that choose A, B, C, D, where A, B, C, D are remainders obtained by such that. So such that का meaning है, you have to consider A, B, C, D as remainders such that their values mod of A, mod of B, mod of C, mod of D are less than k by 2. Do not consider them as values remainder greater than k by 2. Are you getting? So Therefore, here I have written, consider the remainders r if r is less than k by 2. But if r is greater than k by 2, then the consider value as mod of r minus k. So that is what we are doing over here. See, mod of 6 minus 7 is equal to mod of minus 1. Mod of 5 minus 7 is equal to mod of minus 2. Okay, so like that you have to choose the integers a, b, c, d, so that we get our required result. Okay, so with this now we proceed further. So since mod of a is less than k by 2, mod of b is less than k by 2 and so on, obviously squaring both the sides we get the equation 2. So here is the equation 2, that a square is less than k square by 4, b square is less than k square by 4 and so on. Okay, so now from this, if all this, if you square both the sides, then you and add all those congruence equation, then you are going to get x square plus y square plus z square plus w square is congruent to a square plus b square plus c square plus d square modulo k. But we know that x square plus y square plus z square plus w square is congruent to 0 modulo p, because that is what we have considered. It is equal to kp, correct? From equation 1, we have considered that this sum kp is equal to x square plus y square plus z square plus w square. So this sum is congruent to 0 modulo p. But this sum is equal to kp we are considering. Therefore, it is also congruent to 0 modulo k. Okay, and therefore this a square plus b square plus c square plus d square, we can say it is congruent to 0 modulo k. That means this sum is divisible by k. So we can say let it equal to nk. So it is equal to nk. That means here nk is expressed as sum of 4 squares. Now students, we have to obtain the result that there exists some integer k, there exists some integer n which is less than k, and which can, so that nk can also np can also be expressed as sum of 4 square. So we are going to make use of this equation over here. Okay, so remember this. So now here we are getting nk is equal to sum of 4 squares, where what is your what are your a square, b square, c square and d square? Each one of them are less than k square by 4, and therefore we can say this sum is less than 4 times k square by 4, and therefore here we get n is less than k. So now we have got an integer n which is a positive integer less than k, and nk is can also be expressed as sum of 4 squares. So now our job is to show that NP is also equal to sum of 4 squares, and then we are at a contradiction, because we have already got the number n which is smaller than k, and we so that nk is also equal to sum of 4 squares. So now if we show that np is also equal to sum of 4 squares, then we get the integer less than k, where np is also expressed as sum of 4 squares, and that is a contradiction to the other, value of k. Okay, so that we get on the, so for the time being, just remember that nk is a sum of 4 squares and n is an integer, therefore n is an integer which is less than k. Okay, so now let us move to the next page. So now consider nk into kp. So we know that nk is equal to a square plus b square plus c square plus d square, and kp is equal to this. We know that from equation 1. Okay, so if we simplify this, we are going to get k square into np, which is equal to the product of two numbers where each number is a sum of 4 squares. So by Euler's lemma, this product also can be expressed further as sum of 4 squares. So here we have denoted that by the values x square plus t square plus u square plus v square. By Euler's lemma, you get all these values. So please refer to Euler's lemma. You have to remember that Euler's lemma. So you get the value x, t, u, v in this fashion. Okay. So now consider s. S is equal to ax plus by plus c z plus dw, but now x is congruent to a modulo k, b is congruent, y is congruent to b modulo k, that we have seen, assumed in the or we have got it on the previous page. So you can just refer to your notes. X is congruent to a modulo k, y congruent to b modulo k, and so on. And therefore we are using that over here. So putting that value, we can get this sum is congruent to a square plus b square plus c square plus d square modulo k. But this sum is equal to nk. Okay, and there, since this sum is equal to nk, this is congruent to 0 modulo k. So what we are getting, that x is congruent to 0 modulo k. Now consider t as ay, bx, cw, dz. Now again use the same thing. Y is congruent to b modulo k, x is congruent to a modulo k, w is congruent to d modulo k, and z is congruent to c modulo k. So by substituting that value, you can get see that t is congruent to 0 modulo k. So in the similar fashion, you can get u is also congruent to 0 modulo k, v is also congruent to 0 modulo k. So that means each of x, t, y, u and v are divisible by k. So since they are divisible by k, we can say x upon k, t upon k, u upon k, and v upon k are integers. Okay, so now from 5, equation 5, you have it that in your notebook. Please refer to it. So you get np into k square is equal to this x square plus t square plus u square plus v square, and therefore this we can modify in this fashion. Okay, so after this, what we are getting, np is equal to sum of 4 squares. So now we have reached to our last part of the theorem. Okay, so I will open the page number 40. So we have got nk as a sum of np as a sum of 4 squares, but from 4, see that what I explain you there also. From 4 we have the value that 0 is less than n less than k. So here we have got np as a sum of 4 squares, where the value of n is less than k, which is a contradiction, because we are saying k is the smallest positive integer, such that kp is equal to sum of 4 squares. Okay, therefore k cannot be odd such that k is greater than 1. So k cannot be even, k cannot be odd such that k is greater than 1. But we have the value for therefore but k is an integer, therefore k cannot be even, k cannot be odd greater than 1, and therefore then k must be equal to 1. And therefore, so since k is equal to 1, we get that we have the equation that kp is equal to x square plus y square plus z square plus w square, but k is equal to 1, and therefore we can say p can be expressed as sum of 4 squares, not necessarily all are 0. Okay, now from this result, we get theorem 4, that every integer n can be expressed as sum of 4 squares, not necessarily all are 0, because every integer n we can write as product of prime numbers. Okay, so when we write it as a product of prime numbers, these primes may be distinct, may not be distinct, but then we know that each of the prime can be expressed as sum of 4 squares. And then by theorem 3, that is by Euler's theorem, we know that if we have the product of two values where each value is a sum of 4 squares, then that product also can be expressed as sum of 4 squares. So using this 3 and 4, inductively we can get that every integer n can be expressed as sum of 4 squares, not necessarily all are 0. So if the theorem 4 is asked, then you have to write down the proof of theorem 4, and you have to mention the statement of the theorem 3. Okay, so using that we get this result. Now in the next lecture, that will be a live session, we will solve problems on this part. Thank you very much.